Folks, tonight we have an inequality with a strange looking constant on the right hand side, and I say that because if this was behaved like a polynomial, you never would be able to say for all x. But this inequality holds for all real x. You know what I mean? What I'm trying to say here is that if I look at something like this a priori, I would expect there to be some dependency on x on the right hand side of the inequality, but it turns out for all real x, this left-hand side has an upper bound of the square root of 78. Now let's get busy showing why that's true, because the Cauchy-Schwarz in a little bit of algebra will actually show why this is true in a fairly elementary fashion. What we can do, and this is just sometimes called the one trick for the Cauchy-Schwarz, you can prepend a 1 to each of these expressions. Okay, so everything can be multiplied by 1. That's just the multiplicative identity. Nothing wrong with that. But in the Cauchy-Schwarz inequality, we can take the 1s to be the a sub i's, which are coordinates of a part of the coordinates of a vector, if you want to think of it that way. So the a sub i's are all equal to 1 here. Okay, and of course we're dealing with the case n equals 3 here for the Cauchy-Schwarz. So again, you can think of the Cauchy-Schwarz is taking a vector. This would be the inner product of a vector squared is always going to be less than or equal to the product of the magnitudes of the vector squared. Okay. Now we'll take the b sub i's just to be the algebraic expressions, the radical terms, and we'll go ahead and fill it in on the Cauchy-Schwarz here. Now notice that the 2 that you see right here is exactly the 2. We'll have to take the square root, but that turns out to be not so messy. All right. Then all the a sub i's, they get squared. I wrote that down for emphasis, 1 squared plus 1 squared plus 1 squared. Okay, and then these objects are all square roots of some algebraic expression. And so when you square the square root of something, you just get the radicands back. Like you see right here, when this got squared, all that's left is the radicand. You can see it right here. When the square root of 13 minus x squared got squared, all that's left is the radicand 13 minus x squared. Okay? Now, notice we're still in this form right now. Now, when we go to here, we're actually taking the square roots of both sides. When we go to this next line, we're taking the square roots of both sides so we can get to the expression we're actually trying to find an upper bound for. Okay. Now, the first algebra piece of algebra that really saves us here is when you expand this out right here, x plus 1 over x quantity squared, you get x squared plus 2 times x times 1 over x. But x times 1 over x is just 1, right? And then, of course, we have plus 1 over x squared. That's this piece, just expanding this piece out right here. And of course, that's what I have written down right here. See, the x's cancel, and then you have the 2 that you see right here. This 2 right here is this 2 right here, because the x's cancel, right? Okay, and of course, I summed up the 3's. There's a square root now because we took the square roots of both sides of the general form. Okay, so where does this lead us? The rest of this is just consolidating, collecting like terms. Okay, all the constants from up here added up to 24. Okay, this constant 4, 13, and 7 added up to what, 22, and then when you add this 2 to this 24, you get this statement right here. And this, of course, is equal to the square root of 78. So we proved what we set out to prove. It's an absolute max. Now, I wasn't trying to find out where the max occurred. I think you can do that by, if all of these guys lie on the same line, if the ratios of the I8s, well, let me just write it up here. The equality condition would happen if you had something like this, a sub 1 equals to lambda, let's say. That's the letter you see a lot of times in linear algebra, times b sub 1. Okay, if there's a lambda like that, where they're all, and this should be b sub I, that would be the equality condition. And I don't know if I haven't even tried it yet, but that's not what I was trying to do. But there is an equality condition where you can set, if they have this relationship, then you can find out exactly where the maximum value occurs. It may happen in more than one spot. But in any event, my goal is just to show you that the entire expression is less than or equal to root 78 for all real x, which to me is kind of amazing. But it's just that the problem's kind of rigged to work when you see how this gets expanded related to the rest of the terms on the left-hand side. So anyway, we can write down QED here. Okay, that's all for tonight.